In section 4, we're going to talk about comparing two populations. So we're going to talk about calculating a confidence interval and a significance test. So when we're comparing two proportions, when doing random sampling or even a randomized experiment, it's a very common situation, and what we're looking to do is to determine whether the two treatments cause the observed difference, and we want to draw a conclusion about the population for all subjects. So first thing I want to do is review the conditions when we were doing a sampling distribution P1 hat minus P2 hat. So for this shape, the shape was normal as long as N1 times P1 was greater than or equal to 10. N1 times 1 minus P1 was greater than or equal to 10. Then we did the same thing for N2. So N2 P2 was greater than or equal to 10, and N2 times 1 minus P2 was greater than or equal to 10. For the center, that was when we had random. So both of our populations had to be taken randomly, and then we said the mean of P1 hat minus P2 hat was the mean of P1 hat minus the mean of P2 hat. And then for spread, that was when we had independence. So that was when sample 1 had to be less than or equal to 10% of its population, and sample 2 had to be less than or equal to 10% of its population. And as long as that independence condition was met, we said the standard deviation of P1 hat minus P2 hat was equal to the square root of P1 times 1 minus P1 all over N1 plus N2 times 1 minus, P2 times 1 minus P2 all over N2. I'm not going to make you check conditions for a difference in proportions for a confidence interval or a significance test. But again, you will still have to know the conditions in case of a multiple choice question. So when it comes to calculating the confidence interval for a difference between two proportions, it follows the same rule as a regular confidence interval. You do your statistic plus or minus your critical value times your standard deviation. But this time our statistic is P1 hat minus P2 hat. So it becomes P1 hat minus P2 hat plus or minus our critical value Z star times our standard error, which in this case is P1 hat times 1 minus P1 hat all over N1 plus P2 hat times 1 minus P2 hat all over N2. So the Z star is still our critical value, and we calculate it using INV norm just like we did for a single proportion. And then we don't care about if we do the tail to the left or the right, because that plus or minus takes that into account. And then instead of being a 1 sample Z interval, it is now a 2 sample Z interval for a population proportion. Let's go ahead and look at an example. So as part of the Pew Internet and American Life project, researchers conducted 2 surveys in 2012. The first survey asked a random sample of 799 U.S. teens about their use of social media and their internet. A second survey posed similar questions to a random sample of 2,253 U.S. adults. 80% of the teens and 69% of the adults used social networking sites in these 2 studies. Construct and interpret a 95% confidence interval for the difference between the proportions of all U.S. teens and adults who use social networking sites. So similar to when we were comparing the sampling distributions, our first step always has to be define our P1 and our P2. So I'm going to let P1 be teens and P2 be adults. Right? When you are trying to determine what P1 and P2 are going to be, it does not matter. I typically always define my variables so P1 is always the bigger proportion so that my confidence interval does not contain negatives if possible. It just lowers the chances. It doesn't make it 100% sure that it's not going to contain negatives. It just lowers it. It's not wrong to have a confidence interval with negatives for a difference in proportions. It could still happen. It would just mean that, that's the case when your second proportion is more likely than the first. Then we do our critical value. So for a 95% confidence interval, it's 1.96. I don't have to calculate P1 hat or P2 hat because they are given to me. I still like to identify P1 hat, and I do like to differentiate between N1 and N2. That way when I do the interval, I have my P1 hat and N1 together and my P2 hat and my N2 together. That way I don't have to go back and keep looking through the problem for the information. So this is not necessary, it's just helpful when you're setting up your formula. So when we do P1 hat minus P2 hat, we'll do 0.80 minus 0.69 plus or minus 1.96, and then the square root of 0.80 times 1 minus 0.80 over 799 plus 0.69 times 1 minus 0.69 all over 2253. Similar to when I do a regular confidence interval, I like to do it in steps. So 0.8 times 0.69 is going to be 0.11 plus or minus. And then again, I am going to type this whole thing in my calculator. Again, you're going to want to, depending on your calculator, you want to be able to do the fraction button so that when you are typing what's underneath your square root into the calculator, you are doing it correctly and have parentheses in the correct place. If you're not sure how to do that in your calculator, let me know and I'll help you. And I'll make sure that if you don't have that ability, you can do the parentheses correctly. So it becomes 0.0337. So then I do 0.11 minus that number and then 0.11 plus, and that will give me the confidence interval 0.0763 to 0.1437. And the last step is to write our sentence. So it starts the same way as a regular confidence interval. We are 95% confident that the true difference in proportion between teens and adults who use social media and the internet is between 0.0763 and 0.1437. And similar to when we did the sentence for a single confidence interval for proportions, you can convert your confidence interval to percentages when you write your sentence. I don't care if you leave it as a decimal or percentage, but just make sure that you are using the context of the situation when you are writing your sentence. So the last thing we have to talk about is a significance test for a difference in proportions. So for the null hypothesis, we are always going to state that the proportions are equal to each other. So that would mean that there is no difference between our two proportions. Our alternative hypothesis can then either be that one of them is bigger than the other or that there is no difference. So our alternative hypothesis could be greater than, less than, or not equal to. So greater than, less than, or does not equal. The other way you can always write this is as a difference. So we could also say P1 minus P2 is equal to 0. So that means that they are the same. You could also say P1 minus P2 is greater than 0, P1 minus P2 is less than 0, or P1 minus P2 does not equal 0. These all are acceptable ways to do the null and alternative hypotheses for a difference in proportions. So for our test statistic, it is calculated a little bit differently for the standard deviation than it is for a single. So for our test statistic, our numerator is going to be P1 hat minus P2 hat. We don't actually have to subtract our null hypothesis like we did for a single proportion. And that's because our observed difference is always 0 for a difference in proportion. So our numerator is just P1 hat minus P2 hat. For our denominator, when we are doing our standard deviation, because it has to be based off of the population, we don't actually use our test statistic. And because our observed difference is always 0, we use something called the pooled proportion in calculating our test statistic. So it ends up being PC hat times 1 minus PC hat over N1 plus PC hat times 1 minus PC hat all over N2. So PC hat represents the pooled proportion. And what that does is it only cares about the successes from each of our proportions. So the way that it's calculated is N1 plus N2, and then it is the number of successes from P1 and P2. So you would do P1 successes. So we would say it would be x1 plus x2, where x1 is the number of successes in P1, and x2 is the number of successes in P2. Okay. And then our p-value is calculated the exact same way using normal CDF. So you do normal CDF, you do your lower and upper bound, your mean is still 0, your standard deviation is 1. And again, just like for a single one, if the alternative hypothesis does not equal, you have to double the probability that you get. If it's just less than or greater than, you just use what you get from normal CDF. So this is called a two-sample z-test for a population proportion. And the most time-consuming part is calculating that test statistic. So you want to make sure that when you do the practice, you are double checking that you can plug it into the calculator correctly. All right, we are going to do one example of this. So researchers designed a survey to compare the proportions of children who come to school without eating breakfast in two low-income elementary schools. An SRS of 80 students from school 1 found that 19 had not eaten breakfast. At school 2, an SRS of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. Do these data give convincing evidence at the alpha equals 0.05 level of significance level of a difference in this population proportions? So I have to define my P1 and my P2. So P1 is going to be school 1, and P2 is going to be school 2. So my null hypothesis is that the proportions are equal. So P1 equals P2. For the alternative hypothesis, it does not specifically state in any part of the question that we want to know if the proportion is higher or lower at either school. We just want to know, is there a difference in the proportion? So in the last sentence it says, is there a difference in the population proportions? So this is telling me that my alternative hypothesis is does not equal. So I need to calculate my P1 hat, I need to calculate my P2 hat, and then I need to calculate my pooled proportion. So P1 hat is going to be 19 over 80, which is 0.2375. P2 hat is going to be 26 over 150, which is going to be 0.173 repeating, so 1733. And then for my pooled proportion, my x1 and x2 are my number of successes, so 19 plus 26 over 80 plus 150. So 19 plus 26 is 45. Over 80 plus 150 is 230, which is 0.1957. And again, when you're doing your test statistic for this, if you want to leave P1 hat, P2 hat, and your pooled proportion as fractions, because 2 of the 3 decimals are not nice decimals, you can. But as previously stated, going for decimal places gives us an accurate enough test statistic that it isn't going to change our answer or our conclusion. So for our test statistic, our numerator is going to be 0.2375 minus 0.1733 over, in our denominator, the square root of 0.1957 times 1 minus 0.1957 all over our first sample size, 80, plus 0.1957 times 1 minus 0.1957 over the second sample size of 150. Probably the hardest part of a difference in proportions is that pooled proportion and remembering to do it for the denominator of the test statistic. Because when we're doing a difference in proportions for a confidence interval, we don't have to do it. And when we're doing our significance tests, when we're doing our sample proportions before in chapter 5, we also didn't have to worry about it. So it is something new that you're going to have to get used to. Also, not something I'm going to make you memorize. So remember, I do give you the formulas on the quiz, so you do not have to memorize the formula for the pooled proportion or the test statistic. So we're going to get 1.17 after plugging that into our calculator. So now we go to normal CDF. Our lower bound is going to be 1.17. Upper bound is the 1E99. Mean of 0, standard deviation of 1. And we get 0.1210. So for our p-value, because our alternative hypothesis here was does not equal, we do have to multiply it by 2. Which is going to be 0.242, which if we compare to our alpha is greater than 0.05, which means we are going to fail to reject our null hypothesis. So for our sentence, there is not enough evidence to show a difference in the true proportion of students at the two schools who do not eat breakfast. So please let me know if you have any questions about doing a confidence interval and a significance test for a difference in proportions, especially when it comes to calculating the test statistic for a difference in proportions.